What's up, scholars? Hope you guys are enjoying your e-learning. Today we're going to continue our discussion of series. We're just going to talk about geometric ones this time. We, of course, remember that sequences are an ordered list of numbers. And we took notes about geometric sequences previously when I just kept going on for a while. I thought we were going to get there that last lesson, then realized that last video was 30 minutes, so had to cut it off. Come back for part 2. Geometric sequences. What are they? They are a series of numbers where the ratio between the consecutive numbers is constant. You're going to look for a general formula that's being multiplied or divided by the same number. Speaking of general formula, it's going to be a sub n equals a sub 1 times r to the n minus 1, where a1 is the first term, r is the ratio between the terms. And we had an example here where we started with 7 and we multiplied by 3 every time. And then we started with 7 and we multiplied by -2 every time. So let's continue on our investigation of geometric series. Sequences, geometric sequences. Series will come later. Geometric sequences. So we're going to start off with a little game I like to call, Is the Sequence Geometric? If so, find a sub 1 and r. It's a great little game. Here's our first question. First question. Sequence. 5, -15, 45, -1, 35. Is the sequence geometric? Well, what does it need to be geometric? The ratio between consecutive terms has to be the same, so let's say I take the second term divided by the first term. -15 divided by 5 is -3. The ratio between these two, 45 divided by -15, is -3. And -135 divided by 45 is -3. So I'm going to go ahead and say, yes, the ratio is the same. The ratio is -3. And a1 is the first term, which is 5. Let's play round 2. Here's round 2. 8, 4, 2, 1, 1/2. Let's see, ratio-wise, what do we got? 4 divided by 8, we can already tell. This is a half. Each one of these is a half as the other one. Right? 4 divided by 8 is a half. 2 divided by 4 is a half. 1 divided by 2 is clearly a half. 1/2 divided by 1. Anything divided by 1 is itself. That's a half. So, for sure, our ratio is 1/2. And our a sub 1, first term, best number in the world, 8. Which brings me to question number 3. Alright, scholars, question number 3. Sequence. Is it geometric? 3 squared, 3 to the 4th, 3 to the 6th, 3 to the 9th. Why do I insist on writing so small? Sorry. Well, you know, my gut says no because the last 2 were yes. But then sometimes, you know, I just make all 3 of these yes. So you can't really trust me on that part. We're just going to have to do the work here. The ratio, oh, this is such a good question. Asking us to do a couple things here. Ratio of 3 to the 4th over 3 squared. 3 to the 4th over 3 squared. These guys have the same bases, so I can do what with the exponents? I can subtract them. 4 minus 2 is 2, so this is 3 squared. That's the ratio between those two. Now I realize the pattern. Right, I'm going to take that exponent minus that exponent to get the ratio. We're going to run out of space, so I'm going to go up. 6 minus 4 is 3 squared. We're looking good. Those are the same ratios, but then 3 to the 9th over 3 to the 6th, that is 3 cubed, so no. No common ratio. Gut was right. Should have stuck with it. Alright, cool. Thanks for playing that game of Is the Sequence Geometric? Let's play another game called Find the Formula. We've got a sequence here. We're going to find the explicit formula for it and then find the 14th term. This is another great game. You're going to love it. All right, well, what's the general formula of a geometric sequence? It is, of course, a sub n equals a1 times r to the n minus 1, where a sub 1 is the first term, and we see that our first term is the number of fingers on your hand, if you have a normal number of fingers, which is 5. The r stands for the ratio between the numbers. So we've got negative 10 divided by 5. That's definitely negative 2. 20 divided by negative 10. That's definitely negative 2. Okay, cool. Great. R is negative 2. So we've got everything we need for our formula. A sub n equals a1, which is 5, times our ratio negative 2 to the n minus 1. That's it. This is probably something you haven't seen before, the n minus 1 thing. Let's talk about that for just a second, why that exists. Let me turn my phone off. Ooh, unprofessional. Why does that n minus 1 exist? Well, think about our first term was 5. It's just that guy right here. So we want our first term, when we plug n in, we want our first term to be all that's left. So we really want this term to go away. So if we make this exponent to the n minus 1, when we plug n equals 1 in, we get 1 minus 1, which is 0. And anything to the 0 power is 1, so we have 5 times 1, which is 5, which is our first term, which is why that n minus 1 is what that n minus 1 is. Anyway, the other part of this question for real is, what's the 14th term? Well, this time we're going to plug in 14. 5 times negative 2 to the 14 minus 1, aka 5 times negative 2 to the 13 equals 5, I don't know what negative 2 to the 13 is. I'm going to have to use a calculator on that one. Turns out to be 5 times negative 8192, a huge number. 2 to the power of things comes up a lot in computer science, since you have two options, on and off, existing in that binary language. But anyway, yeah, negative 2 to the 13th is a huge number. Times that by 5, even larger. Negative 40,960 is the 14th term of that sequence. Alright. That was such a good game, we should play it again. Oh yes, there's a part B. Same question as before, what's the explicit formula? Oh, weird. I see what I did there. This isn't really part B, this is like example 3. Ah! Example 3. Crazy. Anyway, let's find the explicit formula. And let's go ahead and find the 20th term this time. Alright, what's our general formula? A sub n equals a1 times r to the n minus 1. And we know our first term is 2, and our ratio is 6 divided by 2 is 3. R equals 3, so our explicit formula, a sub n equals 2 times 3 to the n minus 1. And the 20th term will occur when we plug 20 in for n. 2 times 3 to the n, which is 20 minus 1, is the same as 2 times 3 to the 19th power, which is 2 times 3 to the 19,683 times 2 is that right? I don't think so. 3 to the 19. There we go. I knew that was crazy. That was way too small. This, in fact, is 2 times. Holy cow. Are you ready for this? that's got 3 commas. 1 comma, 162 comma, 261 comma, 467. What does that make that? 100,000 million billion dollars times 2, of course. 2, 3, 2, 4, 5, 2, 2, 9, 3, 4. Large number in 20th term. Okay, this next game is called Find the Missing Terms. Where'd they go? Why'd they leave? I don't know. We're gonna find them though. Let's say we know this is geometric, since this is part of the geometric sequence video. So we're gonna go ahead and use the general formula for geometric to try to figure out what our missing terms are. So our general form says a sub n equals a sub 1 times r to the n minus 1. We know the first term is 45. We don't know the ratio, because I can't do a2 divided by 45 and get anything meaningful. So that's what we're going to have to figure out first. But I do know the 1, 2, 3, 4th term, whoops, is 360. Let's see if I can make that work. 360, sure. That was the 4th term. So we're still plugging in 4 there, even though it's minus 1. Right? That was important so that we could get for our 1 minus 1 just that a1 term left over. So we're still plugging in 4. Don't let that make you feel funny, weird about it. Alright, so let's just do some simple algebra. 360 is 45 times r to the 3rd. We're going to divide by 45 on both sides. 90 goes into 360 4 times, so 45 must go in there 8 times. 8 equals r cubed. Gosh, dang it, 8 is the best number. There went my pen cap. Anyway, we're going to cube root both sides because we can. And we're going to get that r equals 2. So nice. Alright, cool. So now we have our general formula, which says a sub n equals a1, which was 45 times 2 to the n minus 1. And we need a 2. So we do 45 times 2 to the 2 minus 1 is 45 times 2 to the 1, which is just 2. 45 times 2 is 90. Oh! Or we could have used the fact that we know r is 2, couldn't we? That means we're multiplying this guy by 2. 45 times 2 is 90. Well, let's just use that fact and quickly get a3, which will be this guy times 2, which is $1.80. Which makes sense because this guy times 2 is a whole circle, 360. Man, that's a good game. Let's play it one more time, shall we? Yes, definitely. All right, round number 2. Our geometric series sequence. Our geometric sequence is 12.5, A2, A3, A4, 5.12. Oh my gosh, Miss Ekin, there are decimals in this problem. Yes, it's okay. It's all good. It's the same stuff. Don't sweat about it. A sub n still equals a sub 1 times r to the n minus 1. Right? That's cool. We still know the first term already is 12.5. We still know that the 5th term is 5.12. It's like not even hard. Right? We do a little division of this guy. And also reduce that guy. Right? Not even a big deal. In which case you get 0.4096, which will be a number recognizable to people that were really good at the game 2048, equals r to the 4th. Okay, doing fine. We're going to 4th root both sides. fourth root both sides. And we're going to get 0.8 equals r, which you can leave as a decimal if you want. You can also recognize that that's a pretty common fraction of 4/5. And, you know, either one's cool here. So our general formula, a sub n equals 12.5 times 0.8 or 4/5 to the, what was our r? Just kidding, that was our r, right? So we're n minus 1, so it goes right there. Great. Now we need to find a sub 2 and a sub 3 and a sub 4, which sounds like time for a little movie magic. I hope you all had a great game. I found that a sub 2 was 10, a sub 3 was 8, a sub 4 6.4. Alright, we're ready for one last game called Putting It All Together. We're going to identify whether the sequence is arithmetic, geometric, or neither, and then identify its explicit formula and the next two terms. We've got two sequences here, 21, 0.5, 0.25, and 25, 50, 75, 100. I'm going to set the timer for 30 seconds. Let's see what we can do. I think we did pretty good. I think we should try that one more time. Kind of like that music. Here we go. Woohoo! Just barely. Nicely done, scholars. Great work. Good lesson. Y'all are doing wonderful. Hope things at home are going along swimmingly. Come hang out with me in my office hours. And, you know, keep on that hustle. Love ya. I'll see you next time.